Okay, now let's visualize the tree we've made. So to do so, we use the export graph viz function from scikit-learn. We imported it at the top of this notebook and we pass a few things. So first we need to pass the tree we have trained. So we pass that. Then we pass, actually before I go through the rest of the arguments, let me tell you what this does. So what export graph viz does is it takes in a tree as input and then it's going to output the string in dot format, which is a string representation of the tree. I'll actually show you what that looks like when we do this. So it's a string. It's just a bunch of text that represents the structure of the tree. So that's what it's going to do. So we pass it the decision tree. Then if you'd like to actually write the dot string to, or the dot format, sorry, the dot format string to a file, you could put it here. So here we're saying none. So we actually want to return that to a variable, which I'll show you in a minute. And then we can set some options. So if we like the nodes on the tree to be filled with a nice color, then we can set filled to true. If we like, and you'll see this very soon, if we like the nodes to be rounded instead of square rectangles, we can do that. And then, so these two are just aesthetic. And then this one, we can pass the feature names, which can be very helpful to see in the tree. So you'll see that very soon. So let's go ahead and actually, so that's what this line does. So this creates the string. In fact, yeah, let's run this and I'll show you what that looks like. So let me just show you this part. So see how it's a string, right? And this is actually encodes the structure of the tree. There's different colors, there's where the branches are, all this stuff. So it's a very long string that encodes the structure of the tree. So we can then convert this to an actual image. And to that we use GraphViz. So GraphViz is the library we installed at the beginning of this week. And it will read this text and it can actually make it a graphic. So we just pass this text to it. We say the format that we'd like the image to be, and that returns this GraphViz object, which we can then save to a image. So this is the GraphViz object. And then we just use the render method to save it somewhere on our computer. That's the image save path I have here. And I am just making that image save path the current working directory that we are in. So wherever we're running the notebook, it will save it in that directory with the name dt_1, which just means decision tree 1. So I've already run this, so let's go look at it. So here, this is the directory that contains the notebook that we've been running. Here's the notebook there's the notebook we've been running. And then here's the output. So this is actually the string that we've already seen. It outputs that as well. And then here's the image. Let's open it. See what kind of monster we've created. So this is the decision tree we have created. It's big, and I told you they could be big. See all these splits, and then at the very bottom we have these leaves, right? Every box where a mouse is that isn't a split, these are all leaves. And I'm going to zoom in a minute, but you can get the idea how crazy a tree can be. And this actually isn't even that crazy. But let's zoom in, take a look. Okay, so the first split is failures. And the reason we have the names of the features here is because we pass the names here. If you don't pass these names, it will have like x1, x2, x3, etc. So it's always good to pass the names. It makes it much more readable. Okay, so this is the first split, and the question, right? The true or false statement is failures less than 0.5. So what is knowing our data? I should say less than or equal to knowing our data. What does this mean? Well, we know there's only 5 options for failures, right? There is 0, 1, 2, 3, and 4. So what this is really testing for is, does the student have failures or not, right? Because less than or equal to 0.5 really means, is it 0? That's the only option, right? The only option in our data less than 0.5 is 0. So if this is true, it means the student has no failures. And If it's false, it means the student has failures. So these are all the students in our training data, all the rows where the students had a failure get pushed to this part of the tree. All of those where they had 0 failures get pushed over here. So let's go over here. These are students that do not have failures. So then it wants to split on, do they go out? And we had different levels of go out. So if the level is, 3 or less, then we go over here. If it's greater than that, we go here. So you can see you do have to interpret the tree a little bit. You have to know that there isn't really a value. There isn't really a 3.5 value of go out. This is really, knowing our data, we know the levels of go out that we don't have. The levels are, 0, 1, 2, 3. I actually don't remember, but I know it's integers, and we can look at that in a second here. Same with age. We know our ages are all integers. So you do have to interpret this. And let's look at some other ones, though. Let's look at some of the dummy variables. So here, actually, let's do this one. Here's a dummy variable. So at this point, the data is being split, and you can see that the split. At this point in the tree, there are 25 samples here. So if you apply this tree to the training data and you follow these splits, so 251 of the rows end up here. That's the samples 251. Then that's split between here and here. 80 of those samples go down here. This is split on weekend alcohol consumption. And 59 of those 80 go over here. 21 go over here. And then of these 59, it's split on age. And then we have 25 here. And this is now split on, do they have internet or not? So if this is a 1, this is a dummy variable. So internet no will be 1 when the value for internet is no. So when this is false, that means internet is 1, right? 1 is not less than or equal to 0.5. So that would go here. But if internet is true, that would go here. So saying that again, at this point in the tree, when applied to our training data, we have 25 students here, 25 rows. Okay. If you then, of those 25 rows, split on internet, the ones that do have internet will go here, and the ones that do not have internet will go here. Now look at this, only one student, of these 25, only one student does not have internet. That's not so surprising. It was only a small number of students that do not have internet, so it's not surprising that out of 25, only one does not have internet. But you can see how this is starting to overfit, right? The algorithm loves to have a leaf that is pure, one sample, and all of those are fails. So let me explain that. One more thing to explain. How do I know all these are fails? Well, it's the values. So the values just list the number of data points for each class. So the first one will be our zeros, which is a fail, and the second will be our 1. So there's 1, 0, 1 failure in this group of 1. So this is one student that failed, but the Guinea is 0, and it loves the Guinea to be 0, right? The algorithm is trying to do that. So that's why it keeps splitting until, look at all these leaves have a Guinea score of 0. So just like we learned earlier, the tree will split on everything it can until it has pure leaves. But look at the size of these leaves. They're very small, right? Sample size of 2, 1, 2, 1, 2. All these leaves have a small sample size. That's a big red flag for overfitting. I'm just exploring it as I talk here. So again, high level, we have the feature and the test, and you have to do some interpretation because you'll get these like less than 0.5, but you know that, right, the value can only be 0, 1, 2, 3, or 4, or you know the value is only 0 or 1, so you have to interpret it intelligently. You can see the number of samples that are being split. So the training data size is 316 samples. That's what we start with here. You can see the breakdown by class. So of the 316, 105 are fails, 211 are passes, and then you can see like the Gini score for this. So you could actually calculate the Gini score just like we did with our equation for these numbers here, and you would get a Gini of 0.44, and then you can just follow the tree. So you could take any row in the training data set, and you could just pick a row and follow this. Look at the row and say, did the student have failures? Okay, let's say they did. So you go here, and you say, well, was the student's age less than or equal to 16.5? Maybe not. They're 18 years old, so it goes way over here. And you'd say, well, how many absences do they have? Did they have greater than 17? Let's say they did. They had 20 absences. And you can go through. But it's clearly overtrained. So now, in the next lecture, we'll actually look at the accuracy of this tree on the training and testing set, and we will see that it is overfit.